All right, this lecture looks at what happens when we take acids and bases and we react them together in a reaction. And this reaction is called neutralization, because what we're doing here is we're taking those reactive H plus ions, or H3O plus, and we're reacting those with the very reactive OH minus. And they like to come together and form water, so we're kind of neutralizing the acids and the bases here. So in neutralization, we say that the acids provide the H3O plus and the bases provide an OH minus. So if we put these two together, the reaction comes out with H3O plus OH minus gives us two H2Os in the end. And since water generally has a pH of around 7, water would be neutral. So we have basically taken the acid and the base and we've neutralized it. We made them non-reactive anymore. So looking at some more examples, we can look at the hydrochloric acid and the sodium hydroxide. So we have HCl and NaOH. These are a 1-to-1 ratio, so we have this H and this OH are going to form HOH, which we normally write as H2O. And the Na and the Cl come together to form NaCl. So we take the H off of the acid and we take the OH from the base and we're going to make water. The other thing that's left over, this, we refer to this as a salt. So in here, that NaCl is really table salt. That's what you usually sprinkle on your fries or vegetables, whatever. But any acid and base that we combine together, we're going to form water and then we're going to form a salt. So the leftover pieces are referred to as a salt. So here are some more examples that we have. Between here we would take and make the H2O using this H and this OH, and then we're left with a KNO3. So this KNO3 is a salt. Moving down to the next one, we're going to take this H and this OH to make our H2O plus LiC2H3O2. All right. Then coming down to the next one, we notice that we have two H's here and two OH's, so we're going to be able to make two groups of water plus MgSO4. And again, this here and this here are our salts, and we've made water. So we're looking at a double replacement reaction, but a specific double replacement reaction that has these H and OH pieces that show that it's a double replacement with an acid and a base. All right, joy of joys, we get to put acids and bases in with our BCA tables. So this is really similar to what we did in the last unit when we were discussing molarity and we were using the molarity equation and the M1V1 equals M2V2. We were looking at that. Now we're just taking and specifying that this is the concentration of a base. This reaction is an acid and base that are neutralizing. So really, we're not changing any of the other information that we've had. We are just looking at applying the molarity the molarity calculations to a BCA table with acids and bases specifically. So first thing that we need to do is, let's see, they are asking for how many milliliters of this 15 molar solution, or 0.15 molar solution of the NaOH are needed to neutralize 25 milliliters of the 0.125 solution. So we don't know our NaOH. We don't know how many moles we have. We have a bunch. So this is going to be our excess. We need to calculate the moles of the nitric acid, the HNO3. So let's zoom in a little bit on this corner so we have room to work. We have our molarity equals moles over liters. We know our molarity is 0.125 equals our moles, which is what we're interested in, over our liters. It says 25 milliliters. Divide that by 1,000 and we get 0.025. Do our math on that and we get moles to equal 0.0031. So we really don't have a lot of moles that we are working with here, but we'll go ahead and put that in to our equation. So we have 0.0031. We have excess. Of course, our water and our NaNO3 are 0. So we're going to subtract out the 0.0031. We're going to be left with 0. The excess, it's a 1-to-1 ratio, so we're still going to use the 0.0031. We'll be left over with excess. 1-to-1 across all of it, so we're going to add 0.0031 here and add another 0.0031 here. So we're left with, all right, so that kind of fills in our BCA table. Now, we know that we are going to need to use the 0.0031 moles of our NaOH. We have our concentration from up here in the problem, so we kind of need to use our equation again to figure out the moles in the milliliters. So let's move our calculations up a little bit so we have some space. We have moles over liters equals molarity. Our molarity is 0.15 equals 0.0031 over x. We have to get x by itself, so we're going to have to multiply both sides by x to get it out of the bottom. So we have x times 0.15 equals 0.0031. Divide both sides by the 0.15. We have x equals 0.021 liters. Now our problem asked for milliliters, so we need to convert this, and it would end up being 21 milliliters. And we convert that by multiplying by 1,000. So doing this BCA table, we used the molarity equation to figure out moles, put it into our equation, worked out the BCA table, then used the molarity equation again to figure out the volume of our NaOH solution that we would need.